will introduce the second part of chapter 9. And of course, still, I need more lectures for it. Then this is just the second part. Today, we will talk about a very important principle in physics, which is called conservation of linear momentum. I mentioned this before. I said, like, usually the conservation laws are really very important in physics, and we have many of these related to energy, related to linear momentum, angular momentum. Also, I will say we have conservation of charge, conservation of mass energy when we will talk about energy equivalence with mass. Okay, but of course it's beyond the scope of this class. Now, I will say we were working on this problem and we said, like, the net force is gonna be equal to change in momentum per unit time, which means here, if in the case when I will have sigma F, which means like these, I'm talking about the external forces. I don't have any external forces on the system. Then sigma F will be 0. And then you're going to say change in momentum over change in time equals 0, which means here, what does it mean, no change in momentum? Momentum is constant, which means the momentum does not change. And here I can say, since change in momentum is 0, P final minus P initial equals 0. And from that you can say P final equals P initial. Then this is the statement of conservation of momentum. In general, okay, I will write M1 V1 for two objects. Usually, okay, this is a vector. When I will talk about a straight line situation, I will remove these vectors because all the vectors, either they're going to be to the right, which means positive, or to the left, which means negative. Okay, then my V1 and V2, they are representing the velocities of the two objects before the collision. And I will use prime for the velocities after. The reason is I'm using a different notation from your textbook. And like, most of the people, they're going to do that because we are going to add more subscripts. Then it's going to be so confusing when you're going to have 2 or 3. Then instead of saying final and initial, and then maybe say also X and Y, you will see that it's like with 3 subscripts, I believe is going to be confusing. Then this is the most, and here I will say this is the general form of conservation of energy. Now, conservation of linear momentum here, it is talking about, let's say, these two objects. And remember the velocities, they can be, here we are talking about what is called first head-on collision, okay, of two pool balls. Then this is going to be something that is head-on, means that they're going to be aligned, their centers, they're going to be at the same line, which means they will not go into 2 dimensions. Okay, then this is just 1 dimensional. I will say this is when I have 1 dimensional. Okay, but we will also talk about when we have, let's say, 2 dimensional. In this situation here, I have 2, we are suggesting maybe 2, like M1 and M2, but we know that if it is pool balls, they're going to be the same mass. But anyway, like in general, and they're going to come, they're going to hit each other during a very short time. Okay, and that short time, okay, we're going to have, like, there is a force between the two objects. Now, this force here, I can say force 2 on 1 and should equal force 1 on 2. Okay, and remember here, I said in general, the two masses, they're gonna be different. Then regardless what is the relation between the masses, it's not just here because I am talking about pool balls and they have equal masses. These two forces are, in Newton's third law, forces. Okay, action reaction force. I am pulling, the earth is pulling me with my weight, I pull the earth with the same weight. And here it's like something like similar. Okay, this force that is going to be between the two objects during the collision, they are equal in magnitude, opposite in direction. And then after that, we might have any situation. Okay, I will say here, the rule is you're gonna see what is really the initial velocities and also the masses. They're gonna be different or equal. One is much bigger than the other. Then this is gonna finally determine for me how they gonna behave after collision. Okay. Of course, here again the same I will say explanation. After collision, they have each different velocities and momenta, but the total is gonna stay the same. Okay, then regardless what I'm gonna have here when I add, and remember we said this is total momentum, okay, of the system, not a single object. And here again, I will consider also the total, okay, momentum of a system, and this is after. Now we know that there are some of the forces, we call them external forces, and there are forces that during the interaction we call them internal forces. Okay, these internal forces, because we said they are action-reaction pairs, then they're gonna cancel when we are going to add all the forces. Then I will say, let's say here, I have an external force. Okay, this is the net forces. Then I have, let's say sigma F, and then I have an external force, but I have F plus 1, 2, and I have minus 2, 1. Okay, these two forces, they're gonna cancel. Then the net force acting on a system is gonna be just only the sum of all the external forces on it. Then the internal forces are not really considered. Now, internal forces cannot change the momentum of the system, and if I have an external force, then it will change the momentum of the system. If I don't have an external, then momentum is conserved. It will not change. Now, here is an example of internal forces, moving component of a system. Like I have here two boats or whatever, like, they're gonna hit each other with, as I said, force from 1 on 2 is gonna be 46, and the other one, force 2 on 1, is gonna be 46. But the thing is that these two forces are really in opposite directions, and this is the reason that they're gonna, okay, they're gonna add up to 0. Now here, I will start solving problems on these systems. One of them, I like to say it is a recoil. Okay, the recoil here, these are really problems that we're gonna find all the way. Okay, recoil, I am a swimmer that I'm gonna jump into a raft, and then I will have a recoil problem. I am in, like I have to fire a bullet from a rifle or from a gun. Okay, the bullet is gonna go in one direction, and the gun is gonna recoil. And one of the most important things is how to actually control that recoil. And you're going to see that this is the reason why we have maybe the weapon is going to be like heavier than the bullet, so that it will not recoil, because if it is it's going to be very light, it's going to recoil with the same velocity maybe, or then this is not recommended, of course. Now here I have a gun. I changed it into a rifle because I didn't find the picture of a rifle. Calculate the recoil velocity of a 5 kilogram that shoots a 0.02 kilogram bullet at a speed of 620 meters per second. Now, these recoil problems, sometimes they're going to cause a confusion, because you should recognize here that you have the gun and you have the bullet embedded inside, and both of them are at rest, which means here my PI is going to be 0 for sure. Now, also, I know that momentum is going to stay the same, then which means that also my P final is going to be 0. And in order for my final momentum to be 0, I know that one of the objects, they should move in one direction and the other one should be moving in the opposite direction, so that they will cancel each other. Then the momenta, they will be equal in magnitude, but they're going to be having opposite directions, so that they will cancel. Then I can say here, I can apply PI equals P final, mg, m for the gun, should times v for the gun, plus mass for the bullet times v for the bullet should equal mg for the gun and vg. This should be g. Okay, Vg prime plus mass of the bullet, Vb prime. And then 0 equals 5 times Vg prime plus 0.02 times 620 meters per second. And then I'm going to get that there is going to be a recoil velocity that it is negative 2.5 for the gun. Then the gun is going to recoil with that velocity. And as I said, one of the most important things is to control that recoil. Okay, here, a system of particles known to have a total kinetic energy of 0. What can we say about the total momentum of a system? Now, when we go for the kinetic is going to be 1/2 mv squared. In order for the kinetic energies to be 0, the velocities, they should be 0. And then I will say all the velocities for all the particles, they're going to be 0. And momentum is m times v. Then I don't have velocities, then the momentum also, they're going to add to 0. Then the momentum of the system is going to be 0. And we're going to see what if it is the reverse. What if my momentum is 0? Can I say that all the kinetics are really 0? We're going to answer this question later in this chapter. A system of particles is known to have a total kinetic energy of 0. What can we say about the total momentum of the system? Okay, now I will say here that the momentum of the system is 0, as I have explained. Now, collisions, I will say here that word collision, it's not going to consider the collisions I am talking about when I have like car accidents. No, it's not. It's going to be two objects that they're going to be going through an interaction for a very short period of time. Then it's going to be an event where I'm going to have two or more objects, of course, but we will deal maybe more with, I would say, two objects, that they are going to be these two objects, they're going to go and they're going to hit each other, they're going to interact, and through that interaction, they are going to act one of them on the other by a force for a very short period of time. We have three major types of collisions: elastic, inelastic, and perfectly inelastic. And we're going to go over all these. Like in collisions that they are really elastic and they are very rare, I will say, kinetic energy is also conserved. Then I will say the first thing is momentum is conserved. Number two, kinetic energy is conserved as well. And usually I will create two equations, one from momentum, one from energy, and I will solve them to find the final velocities of these two objects. Now, since kinetic energy is not lost, no energy can go into heat or sound, no damage caused to either sliding objects, and of course, we said momentum is going to be conserved. Examples here are atomic or nuclear particles with similar charges, magnets with similar poles facing each other. I will say we can approximate also the pool balls to have elastic. And the other example that is really important, it is the collisions. In an ideal gas situation, we consider these as elastic collisions. Now, in elastic collisions, momentum is conserved, but kinetic energy is not. Energy is lost to damage, heat, or sound. I will not say lost. I like to say converted to damage, heat, or sound, and maybe light. I like to say that energy is dissipated, and I will say also converted into forms that can't be reused. And this is why we don't like it. Now, also, there is another type of, like, this is the extreme, like the elastic is going to sit in one extreme, and completely in elastic collision, it stays at the other extreme or the other side. Objects stick together afterwards. This is the sign that this collision is completely inelastic. Okay, then any problem that you are going to notice that there is something talking about object that they're gonna stick together, they're gonna entangle together, whatever, you're going to say that this is completely inelastic collision. A greatest damage and loss of energy, again, like the energy of the system after is gonna be less than the energy before. Examples here, car accidents where cars stick together, a train crash where the cars stay linked, bullet that stays in the target, the ballistic pendulum. Okay, here we are going to derive an equation for elastic collisions. We said here both kinetic energy and momentum are conserved, and then I will say I consider it to be head-on collision, which is gonna create, like, I will say the masses, they're gonna be like their center of masses, they're gonna be on the same level, and then I will say we are going to have what is really called one-dimensional elastic collision. Now, I will say whenever we are going to deal with elastic collision, you're going to deal either with, this is one thing, which is conservation of momentum plus conservation of energy, and I will say here kinetic energy, or I will deal with conservation of momentum. This is the second option, is conservation of momentum plus the derived equation. Okay, now I did show you here the derivation for this equation, and the equation that I'm looking for, it is this one. Okay, you have it in this form or this form. Okay, now I did use conservation. This is conservation of momentum, and this is conservation of kinetic energy. Okay, and then I did here what I did for the second equation. I dropped the 1/2, and then I rearranged the terms so that I have m1 v1 squared minus v1 prime squared should equals mass 2 times v2 prime squared minus v2 squared. And then here, this is a difference between two squares. I remember when I was doing my math, I was enjoying having that difference. And when I will find the difference between two squares, I feel this is right. Oh, this is the best thing because this is going to make it like easier. Okay, then I did this here for both terms. I converted the difference between two squares into v1 minus v1 prime times v1 plus v1 prime. And then also I took the equation, which is here. This is the conservation of momentum. Also, I rearranged my terms, and then I plugged in the value in it. And finally, I have this is v1 plus v1 prime equals v2 prime plus v2. Or like we can say, this is like sometimes we call it like the relative velocity before and after. They should be equal in magnitude, opposite in direction. Yeah, but I like this one here to use it. Here, this is really the derivation that it did show you. Yeah. Okay, then this is here. This is a replacement of kinetic energy, because when you are going to use the conservation of kinetic energy and you have a square, one of them is linear, one of them is squared, this is going to complicate the situation. Okay, let me show you here. I have a problem where I have a proton, and here I have a mass, which is 1.01 atomic mass units, traveling with a speed of 3.6 to the 4 meters per second, has an elastic head-on collision with a helium nucleus that is initially at rest. What are the velocities of the proton and the helium nucleus after the collision? Assume the collision takes place in nearly empty space. Now, I don't need that conversion factor unless I am asking you to calculate the change in kinetic energy, because that one should be in joules, and when we want to have it in joules, then I should convert the atomic mass units into kilograms. In conservation of momentum, you're going to see that I will not use it because I will cancel the mass from my equations. Now, assuming no friction, conservation of momentum, Pi equals P final, mass of the proton times velocity of the proton plus mass of helium times the velocity of helium, this is before collision, should equal mass of the proton times velocity of the proton after collision plus mass of helium, velocity of helium after collision. I will use also the second equation, V proton plus V proton prime should equals V helium plus V helium prime. I have derived this equation from 2, and I will be able here to calculate Vp prime in terms of V helium prime. And then finally, I plug this in number 1. And then finally, I will calculate what is the velocity of the helium after collision, which is this one. And this is the Vp prime, which is the velocity of the proton after the collision. And this is really, I want you to look at, like the helium is 4 times, like as we said here, 4 m's. And the proton is 1 m. And you can see here that the mass, of course, is going to drop. But the thing is, when the target is very heavy, it's going to, of course, after the collision, it's going to move in like to the right in this situation. But the lighter object which was hitting is going to recoil, or is going to change its direction. Now here, consider 2 elastic collisions. A golf ball with speed v hits a stationary bowling ball head on A bowling ball with speed v hits a stationary golf ball head on. In which case does the golf ball have the greater speed after the collision? I will say situation 2. And why is that? Because here you're gonna find that when we have the lighter object that is gonna hit is gonna have less momentum given to a heavy object, then that heavy object is going to have less velocity, whereas I'm going to have more momentum in the second scenario and given to a light object, which means it's going to be more velocity. Then in case 1, the bowling ball will almost remain at rest and the golf ball will bounce back with a speed close to v. Whereas in case 2, the bowling ball will keep going with speed close to v, hence the golf ball will rebound with speed close to 2v. Then it's just like comparing masses and I will say velocities. Two-dimensional collisions can only be solved if some of the final information is known, such as the final velocity of the object. Then here I will say here, I have that object, mass 1, okay? It is hitting that mass 2, okay? And now we are going to have that so okay, this is mass 2. This is mass